Welcome guys, it's just math y'all. Today we're going to look at rational functions and their graphs. So let's get started. Okay, so we're going to analyze rational functions and their graphs, but I just want to back up just a little bit. What is a rational function? What is a rational function? And then we'll get into the analyzing. Well, a rational function is any function that can be written in the form of a numerator or the denominator, where a numerator function and the denominator function are polynomials. Okay, so this is why we study polynomials first. But if you think about functions, what we've done in functions is we did in chapter 2, we just kind of did an overview of functions, and we learned that functions have domains and ranges. We learned that functions can have graphs. We learned that we can add, subtract, multiply, and divide functions and create a new function when we do that. We also learned that we can compose functions, and that creates a new function. And we also learned that we could do a thing called a difference quotient with a function. And we also learned that we could find inverses of functions. Now that's what we did in Unit 2. That was a lot, but that was just generic, all these things that we can do with functions. So then we went into Unit 3, and we started out with quadratic functions and then polynomial functions. Well, both quadratics and polynomials are polynomials, and those are types of functions. And so now we're going to move into a different type of function. This type of function is called a rational function. Now these are complicated, but they're formed from two polynomials, and so that's why we teach polynomials first. In rational functions, you have a fraction where you have a numerator and a denominator. Okay, so now the first thing we always want to do when we talk about functions is talk about domain. And so the domain is an issue with rational functions, okay? And so when you're dealing with rational functions, the domain is always one of the things we have to talk about, okay? So before we get there, let's go to our sheet. You have a handout that has this information on it. Okay, I sent it to you in an email. If you don't find it, go look in the student documents under the upload your work section, under the student documents, and you'll see rational functions and their graphs, and you'll see that. So here we go. So when we start analyzing these rational functions, first what we want to do is we want to get everything in factored form. Okay, and that's why we talk about learning how to factor the quadratics, and we never really talked much about factoring the third degree polynomials or any other polynomials, but you won't have to deal with those. But anyway, first thing we want to do is get it in factored form, and then we want to determine the domain. Now the domain and the vertical asymptotes are related, but let's just do the domain first. The domain is all the numbers except the points of continuity, and determine these continuities. We set the denominator equal to 0 and solve. So that's basically what we're going to do here. So for our first example, we want to determine the domain of a problem that says 8 over x squared minus 7x minus 18. So this is our function. Okay, and so the first thing we want to do is we want to factor the denominator. Okay, now if the numerator was factorable, we'd be factoring it as well, but it's not, so we're just going to factor the denominator, and this is going to give me a plus 9 and a minus 9 and a plus 2. All right, so those are the factors. And so to find the domain, we need to take the denominator and set it equal to 0 and solve. And so by the zero product factor, add 9 to both sides, subtract 2 on both sides. And so these are our exclusions. These are our points of discontinuity. Okay, and so we have -2 and we have 9. These are numbers that we must exclude from our domain. So that's why the domain for this would be negative infinity to -2, -2 to 9, and then 9 to positive infinity. And if you're still struggling with that, remember the number line. If I draw a number line, and I have -2 on my number line, and I have 9 on my number line, my domain is all numbers except those two. So I put a hole there and a hole there. And so my domain is all of those numbers, all of these numbers, all of these numbers. Okay. My domain can be found at any of these three locations. I can find members of my domain from negative infinity to -2, or I can find some from between -2 and 9, or I can find some from 9 to infinity. So that's my domain right there. Okay, so these are the points of discontinuity, and to find the domain, you just set the denominator equal to 0 and solve. So now, what about the graphs? Well, they're called points of discontinuity because they are discontinuous. Discontinuous. Discontinuous means not continuous. There are gaps. Since there's gaps in our domain, then there are gaps in our graph. And that's what makes it discontinuous, okay, or discontinuity. So what happens? Well, there are two types of discontinuity, two types of graphs that we have to deal with. Oops, what's going on here? Here we go. Two types here. The first type are called vertical asymptotes. I don't know why it keeps doing that. There we go. The vertical asymptotes are invisible vertical lines that, well, I shouldn't say vertical. Well, these are vertical. Asymptotes are invisible lines. We have different types of asymptotes, but these that we're talking about right this minute are vertical. Okay, we can also we'll have horizontal and oblique. We'll talk about those in the next video. But vertical asymptotes are invisible vertical lines that act as boundaries. For our graph, for our function. Okay, and then we also have holes, and holes are exactly what they say they are. They're holes. Holes in our graph. So let me show you what a picture of a vertical asymptote is. So if we had a graph, let's do another example. Say we had 1 over x minus 3. Make it really easy here, okay? I'm going to make it really easy here. Now, technically, these are both polynomials. The numerator is a polynomial of degree 0, and the bottom is a polynomial of degree 1, but they are polynomials. They're already in factored form. Okay, so our x cannot equal 3. Okay, so we set the denominator equal to 0 and solve. This is a point of discontinuity. Our domain is every number except 3. So that's negative infinity to 3, 3 to positive infinity. That's every number except 3. So now what does this look like on a graph? On a graph, there is an imaginary, visible, vertical line. Okay, and so now when you learn about these graphs, and we're not doing these right this second, but when we start graphing them, this one is going to look like this. It's going to have a graph. It's going to go in like that. And then we're going to go in like that. And so this vertical line acts as a boundary. It's not the only boundary line we have in this picture, but that's what an asymptote is. It is an imaginary or an invisible vertical line that acts as a boundary. And so when we have a gap in our function, it might be a vertical line. It might be a vertical asymptote. Now, it might also be a hole. So I'll show you one of those in just a second. Okay, but a vertical asymptote is an invisible vertical line that acts as boundaries for a function. And holes are just literally holes in our graph. So let's look at one with a hole. Okay. So now this one is going to have a hole. Another example. Oh goodness, don't know where that came from. This one says f of x is equal to x over x times x minus 9. Okay, now this one's going to have a vertical asymptote and a hole. Let me talk to you about what that looks like. Okay, so take the denominator, set it equal to 0, and we get our points of discontinuity. These are our points of discontinuity right there. Points of discontinuity. Can't do that. Are 0 and 9. Points of discontinuity are 0 and 9. Okay, so now, which one's a vertical asymptote and which one's a hole? Let me show you. Notice somebody might want to cancel those out. That factor produced that number. And it's a common factor. When you have a common factor, that is what produces a hole. Common factor produces a hole. There's a hole at x equals 0. Okay. Now the 9, that one, it produces a vertical asymptote. This one is going to be a vertical asymptote. Okay. So let me show you what this one looks like. So we have our x-axis and our y-axis. Now you're not going to have to do this just yet, but just let me show you so you can kind of see what I'm talking about. Now I've got a vertical asymptote at 9. Okay, and so I'm going to have, this is what this guy's going to look like, and I just know this. So okay, if I plug in if I cancel those x's out and then plug in the 0, then I get -1/9. So the point 0, -1/9 is actually my hole. And so I'm going to have a hole at 0, -1/9. And so when I graph it, it's going to look very much like the other one, except for it's going to have a hole at 0, -1/9. It's a lot like the other one, but it's got a hole. So I've got a point vertical asymptote at 9, and I have a hole at x equals 0. Okay, I have a hole at x equals 0 and a vertical asymptote at 9. It doesn't ask you for the points. That's usually not done. But I wanted to show you how I got that point, even though we don't rarely have to know that information. Okay, so on your sheet, that's part 1 here. We've done this, so you can look at it. Make sure your factors numerator denominators, and the domain is all the numbers except the points of discontinuity. To determine the points of discontinuity, set the denominator equal to 0 and solve. Okay, and then any factor that is common, both the numerator and the denominator will produce the whole, and the other factors produce a vertical asymptote. All right, that's on your sheet. Everything that's typed up is on your sheet. And that is the first part of rational functions: vertical asymptotes and wholes and domain. So I'm going to come back with video number 2, and we're going to talk more about these rational functions.